Welcome to the NPTEL MOOC on parallel algorithms. I am Sajith Gopalan. I am a professor in the Department of Computer Science at IIT Guwahati. In this course, we will be assisted by three research scholars of the Department of Computer Science at IIT Guwahati. They are Mr. Badri Prasad Nanda, Mr. Ranajit Sengo, and Mr. Manas Kumar Panda. This course is on parallel algorithms as opposed to sequential algorithms, that are algorithms to be run on a single machine. Here we study algorithms to be run on multiple machines. Since this course is intended for BTech final year students or MTech or PhD students, I assume you would have all done a basic course in algorithms. When we deal with parallel algorithms, we have to contend with the inherent sequentialities of the problems we consider. I'll make this clear with an example. Consider the house building problem. Suppose 50 men work for 200 days to build a house. That is 10,000 man days of work. If there are 100 men, the house could be built in 100 days. So you have increased the number of workers by a factor of 2 and the time taken reduces by a factor of 2. That is a speed up of 2. If we have 10,000 men instead, can the house be built in a day? The answer is no. This is because the walls can be built only after the foundation is done. The roof can start only after the walls are done. There are inherent sequentialities in the problem. One part of the job has to finish before another part can start. Because of these inherent sequentialities, when we keep increasing the number of workers, at some point we will not be able to increase the speed up any further. Suppose a problem P can be solved in T1 of n time with one processor. Here n is the problem size. Suppose with P processors, the problem P can be solved in Tp of n time. That is a speed up of T1 of n by Tp of n. When we use P processors, we would expect the speed up to be P. But as I said, because of the inherent sequentialities in the problem, many times P may not be achievable. But still, a non-trivial omega 1 lower bound still be achieved. So sequential algorithms run on one processor machines, parallel algorithms run on multi-processors. In sequential algorithms, we try to minimize the running time. This is the same as the total number of instructions executed. That's because there is only one processor. In a parallel algorithm, we have multiple processors. Therefore, the running time is usually smaller than the number of instructions executed. So these are two different parameters. Minimizing one doesn't necessarily mean minimizing the other, and we may want to minimize the both. That is, we might want an algorithm that runs the fastest and uses the minimum number of instructions possible. You could ask certain questions. In reality, multiprocessors tend to have only a small number of processing elements. During this course, we shall see some algorithms that run in order log n time using n processors, for example, where n is the problem size. When n runs into millions, that means using millions of processors. Is there a disconnect from reality? Not quite. That is because we can simulate the algorithm on a real machine. A real machine that has fewer processors can simulate the algorithm that we have designed, assuming a large number of processors. The speed up will scale up accordingly. Therefore, the algorithm that we have designed doesn't go waste. For another, letting the number of processors grow with the problem size allows us to explore the inherent sequentialities of the problem. As in our house building example, when we had 50 workers, we took 200 days. But when we went to 100 workers, the time taken reduced to 100. The inherent sequentialities of the problem are not exposed yet. But when you increase the number of processors to 10,000, then you realize that the problem cannot be done in a day. That's because the inherent sequentialities are exposed. So when you expose the inherent sequentialities in the problems that we consider, we will be able to evolve new design techniques. We will also be able to classify problems according to the hardness to parallelize them. When we talk about designing algorithms, the first question that comes is, what is the model of computation? In real life, we find a wide variety of multiprocessors. Which one of them will we use for designing algorithms? A theoretical model of computation is just a mathematical tool for designing algorithms. When we adopt a model, it should be good enough, a mimic of the real machines. So we shall see several such models in this course. One of them is a shared memory model, which is called the parallel random access machine. We shall also see several interconnection networks, such as arrays, meshes, and hypercubes. We shall design algorithms on all of them and analyze them. A model of parallel computation could be either synchronous or asynchronous. A model is synchronous if all the processors execute in lockstep. The model is asynchronous if they do not do that. That means in a synchronous model, all the processors are fed the same clock. This course deals with synchronous algorithms. We shall study algorithm design techniques and perform analysis of the algorithms that we see, and we shall see several lower bound proofs as well, and we shall also study some complexity of parallel computation. There is a complexity class called Nix class. Parallel algorithms that run in order of log n to the power order of 1, which is polylogarithmic time using polynomial number of processors, are called efficient. This is analogous to the sequential algorithms that run in polynomial time being called efficient. Problems with efficient parallel algorithms form the complexity class NC. It can be shown that NC is a subset of P, but then the question remains, is NC equal to P? This question is still open, like the P equal to NP question. There is a complexity class called P-complete problems for NC reductions, which are the hardest problems for parallelization. We shall take a look at these problems also towards the end of this course. The main textbooks the course will use are one by Joseph Yaya and another by F.T. Layton. Hope to see you there in the course.